We turn now to the subject of trigonometric identities. The three identities that I've put up on the left side of the screen are three identities that you really need to know by memory in order to do math at this level. They just come up over and over again, both in this course as well as the next two, at least the next two calculus courses that you're going to take. It becomes almost impossible to do math at this level if you don't know these formulas. So the first one is cosine squared theta plus sine squared theta equals 1. The second one is sine of 2 theta is equal to 2 times sine theta times cosine theta. And the third one is cosine of 2 theta equals cosine squared theta minus sine squared theta. And by the way, just by convention, I think most of you realize that an expression like sine squared theta actually means I take the sine of theta and I square it. It's just it's technically an idiomatic notation, but that's in fact what it means. There we go. I'll leave that up there. Okay. So knowing these identities, you can actually derive some other ones. Eventually you'll start to remember these, and you really should learn to remember them. But I'm just going to show you how to derive them. If I start with the equation cosine squared theta plus sine squared theta equals 1, and I divide every term in it by cosine squared theta, write this one a little bit neater. If I do that, then what I get is cosine squared over cosine squared is just 1. Sine squared theta over cosine squared theta is tangent squared theta, and 1 over cosine squared theta is secant squared theta. So that gives you the relationship between tan squared and secant squared, and it's very useful because it allows you to convert back and forth between tangents and secants in the same way that this equation up here allows you to convert back and forth between cosines and sines. For the next identity, I'm going to start with identity number 3 and combine it with identity number 1. So let's start with cosine of 2 theta equals cosine squared theta minus sine squared theta. Now, the thing to recognize is that if I take identity number 1 and I rearrange it, I can solve for sine squared in terms of cosine squared and 1. So that gives me sine squared theta is equal to 1 minus cosine squared theta. And by the way, you should get used to using identity 1 in this form where you rearrange it into a form that has either cosine squared or sine squared on the left side of the equation. Once I do that, what I have here is I can rewrite this equation this way. So this is going to be cosine of 2 theta is equal to cosine squared theta minus 1 minus cosine squared theta. And the little algebra, I can rewrite this as cosine of 2 theta is equal to, that's going to be cosine squared theta minus 1, and then minus negative cosine theta just gives me plus cosine squared theta. Sorry, I meant minus negative cosine squared theta. I'm going to get plus cosine squared theta. So what this gives me is, if I move the 1 over to the left side of the equation and combine the two cosines, what I get is cosine of 2 theta plus 1 is equal to 2 cosine squared theta. That allows me to, if I switch the sides of the equation that are on the equal sign and divide by 2, I get cosine squared theta equals cosine of 2 theta plus 1 over 2. Surprisingly, this is actually a fairly useful formula because it allows you to convert back and it allows you to convert a cosine squared into an expression in cosine that's not squared, which is sometimes easier to work with. Based on that algebra that I just did, I challenge you to find a formula for sine squared theta, and if you work through a similar example, I bet you can find one. We can use the identities to solve a variety of problems. So I've put up this example. Let's suppose that theta is an angle in the first quadrant. In other words, it's somewhere between 0 and pi over 2, or between 0 degrees and 90 degrees. And that we know that the tangent of theta is equal to 3/5. Let's find sine of 2 theta. So what I can do here is I can, as we did in an earlier problem, I can show a right triangle with an angle of theta. And we know that since the tangent of theta is 3/5, that means that the ratio of the opposite to the adjacent is 3/5, and I can just put in those numbers like that. So that means that the hypotenuse is going to be 3 squared is 9 plus 5 squared is 25, and that gives us a hypotenuse of square root of 34. So we now know that the sine of theta is equal to the opposite over the hypotenuse, and the cosine of theta is equal to the adjacent over the hypotenuse. Now, the question is to find the sine of 2 theta. Now, I know that some people sort of instinctively are going to write, oh, I know how to do that. Sine of 2 theta must be equal to 2 sine of theta, right? No, that's certainly not true, because it's not the case that all functions are linear. So the correct way to do it is to recall the identity from the previous screen, where we have sine of 2 theta is equal to 2 sine theta cosine theta, which is equal to 2 times 3 over root 34 times 5 over root 34, and that gives us 30 over root 34 times itself is 34, and that equals 15 over 17. So that's the sine of 2 theta. Sometimes we just want to do a problem like this with a little bit more abstraction. So consider the following. Suppose that sine of theta is equal to 4x for all x in the interval negative 1/4 to positive 1/4. I should point out that that restriction makes a lot of sense because sine of anything can never be more than 1 or less than negative 1. So it wouldn't be possible to have a value of x outside this range and have the equation remain true. But knowing that, let's try to write an expression for tangent of theta in terms of x. So even though it looks like I don't have any numbers to work with, the triangle that we've used in the past will still work. So, oops, sorry about that. We can draw a triangle where there's an angle theta whose sine is 4x. Well, what does that mean? All that means is that the ratio of the opposite to the hypotenuse has to be 4x. A pair of expressions that will do that is I can set the opposite side to be 4x and the hypotenuse to 1. It's certainly the case that 4x divided by 1 is equal to 4x. Well, now, using the Pythagorean theorem, I can find the missing leg. Just recall that if a squared plus b squared equals c squared, where c is the length of the hypotenuse, then that means that a squared is equal to c squared minus b squared, and a is equal to the square root of c squared minus b squared. So, using 1 as the value of c, that gives me 1 squared, which is 1, minus 4x quantity squared, which is 16x squared. And now I have all three sides of the triangle, so I can simply write that tan of theta is equal to, it's going to be the opposite over the adjacent, so that gives me 4x over the square root of 1 minus 16x squared.